for the first talk. He's from Warsaw and Poland, and will tell us about coherence manipulation, asymmetry, and thermodynamics. So, let's share.
Hi everyone. I'd like to thank the organizers first. It's a really nice workshop. I'm really happy to be here in Singapore. So today I'm speaking as a sub-speaker. This talk should really be given by Varun, who is a PhD student in our group. Fortunately, he couldn't make it to this conference, so since I'm a co-author of this report too, I'm giving it in his place. He's going to graduate, so he's going to finish his PhD soon. So if you're looking for a postdoc, let me know so I can let him know to send you an email. Yeah, so there's the talk, archive number, it's joined by Varun and also Alex, which is our common boss. So let's start with what is thermodynamics. So thermodynamics, if you spend, I don't know, if you look at it through a straw, like 1 kilometer away, you can think of it as the study of state transformations, right? Like one of the biggest, well, was one of the most important achievements in classical thermodynamics, in my impression, is that, from this study of, you have a gas, what is the equation of state of this gas? Like how does pressure, volume, temperature relate to each other? You can derive from this the maximum efficiency you can extract work out of 2 baths at different temperatures, right? So this Carnot cycle thing that you move at constant temperature and then do adiabatically, constant temperature, adiabatic process, and somehow you get bound the optimum efficiency you can extract work. So I would argue that through this lens, thermodynamics is about state transformations, right? And because we're in a quantum resources workshop, we have to move to quantum. Like how can we study this kind of question in quantum version? So one way to do it, of course, resource theory is the resource theory of thermodynamics. Camille already nicely introduced this, but for people who missed that or need some refresher, this is the refresher. So, I mean, it's gonna be slow, it's gonna be nice. So resource theory of thermodynamics, right? For those who are not aware, you have a system, but it's thermodynamics. So instead of just having a state, you also have a Hamiltonian that describes this system, right? Gives you kind of the energy. And it's a resource theory, so there's the free states, free operations. Here, the free states are Gibbs states because there's this classic result from 70s or something that Gibbs state is the only state from which you cannot extract work by doing unitaries, right? Even if you consider even multi-copy transfer, multi-couple, even if you have access to multiple copies, it's this completely passive state. So that's your free state. Free operations are what is called thermal operations. So what you can do is you can take your system, couple it to a bath at some temperature, right? And in a Gibbs state, you can do a unitary that preserves energy, and then you can trace out the bath. And it's operational, makes sense. It's thermodynamics. And question, well, thermodynamics is kind of about state transformations. Here, the question would be, what are the state transformations allowed under thermal operations, right? So we saw in Camille's talk that we have some idea in some regimes how this looks like. For example, if the initial state and final state is incoherent, so it's diagonal in this energy basis, then we know how this looks like somewhat. But in general, it is a hard problem, and like I believe it is the biggest problem with the resource theory of thermodynamics, at least for me. And so, okay, that's good. But I would argue also this is not the question you should be asking this is not the question you should be asking, because sure, you can do this thermal operation. It looks general, it looks like it's the thing that you can do, but actually there's more, because there's a thing called catalysis, right? In atomic theory, I guess last year, a lot of people were also here, and I was told that last year there was a lot of talks in catalysis, so it's gonna be what I review. And Jordan also introduced catalysis, but there's this thing called catalysis that instead of just doing transformation from rho to sigma by some promo operation, you might also be able to borrow some catalyst state, right? So here I would say that you can transform rho into sigma by exact catalysis. If you can find a catalyst state in a thermal operation so that it's transformed, right? And you get back the catalyst of the same state in the output, so it's everything's good. You can reuse it, and this is why you didn't make catalyst. Then again, like what are the log state transformations? One of the big results I feel is that in 2015, Ganardi and some other guys characterized this transformations basically for incoherent states. So when the initial state, final state is incoherent, these transformations are characterized by a family of three energies. These are the Rényi alpha three energies, Rényi alpha entities. If you know what that means, if not, then it's just a family of three energies that can generalize the classical free energy. Great. But okay, but is this all you can do? Well, not really, because if you are happy with relaxing some conditions, if you don't require exact catalysis, but you allow some correlations in the final state, then you actually have this much simpler characterization. You get back this classical result that if you have two classical states, rho can be transformed to sigma by correlative catalysis if and only if the free energy is ordered. So it's like very nice, very beautiful, everything is pretty. But there's one big thing missing here, I think, is that this result, it works when you have incoherent states, right? And if we want to do quantum thermodynamics, it's like, you cannot ignore coherence, right? So what about transformation with coherence? So it's a hard problem in general, but I think there is one observation that can help us to address this big question. And the observation is this: you have thermal operations. I have thermal operations. And maybe if I don't move too much, yes. I have thermal operations. If you work through the math and stuff, you notice that they are actually covariant operations. So they're invariant kind of, they have this covariance with respect to time translation. They're given by the and so on. And what does this mean? Well, this means we can kind of apply this. Well, yeah. This means that we can relate it to this other resource theory of asymmetry, right? And if I just, I don't know, again, refresh memories or introduce very quickly. And covariant operations are those operations that can be implemented in this way. So you can think of covariant operations as like thermal operations, but you're not restricted to Gibbs states here. You can have any incoherent state. So I can give you any incoherent word, I get covariant operations. There's this link between thermodynamics and asymmetry that is like, if you just want to study the coherence part, you can study asymmetry. So what is this asymmetry thing? In the original formulation, it's about symmetry. You have a group that describes your symmetry, unitary representation. The free states are incoherent states, well, okay, symmetric states. So they are symmetric under action of the unitary. Three operations are covariant operations, this, mu, right? And in thermodynamics, what this applies to, as I said before, the symmetry is general with time translation, so incoherent states are diagonal. and free states are diagonal, free operations are like this. And yeah, you can think of it as thermodynamics, thermal operations, but you get a source of incoherent work. And this would capture coherence limitations in thermodynamics. So yeah, this, I think I have set the stage, I can state my results somewhat. To do this, I need to find two more things, just a little bit more. So there are these things for any state, you can define kind of what kind of frequencies, which frequencies does the state have coherence in. So this should be non-zero. This is the set of energy pairs, energy level pairs, for which the off-diagonal part of rho is non-zero. Conference dinner. So let's call this available coherence, and let's call this thing, this funny thing, J, as reachable coherence. Think of it as the available coherence in multiple copies of rho. Could be weird, looks weird, but turns out you can actually work out if you work out what this thing is, it's just integer combinations of these things in the available coherence. So you can take integer combinations from the positive, negative, positive. And what we showed is that we kind of derived we found a law of, I don't know, coherence processing and asymmetry. Turns out that if you consider correlative catalytic transformations in asymmetry, there is a transformation going from rho to sigma. If the reachable coherence of sigma is included in reachable coherence of rho, this kind of all right, I mean, I define things, I call things reachable coherences, and that's why, of course, it doesn't sound weird, right? That reachable coherence of, you can transform rho to sigma if the reachable coherence of sigma is included in reachable coherence of rho. It's possible, but what, if you look at it, you start it again, you find that this is actually something pretty weird, right? This means you can amplify coherence unboundedly. If rho has some coherence, just a tiny bit, just epsilon bit, and sigma has a lot of coherence, this is saying that you can still do transformation. And this would mean that you can distill coherence, at least in the level pairs where it has some coherence. You can have infinite distillation rate in this setting. So yeah, this is the first result that we found, and I do have some time. Yes, I do have some time, so I'm going to sketch how we show this, right? So what is known, if you're not familiar with resource theory of asymmetry, also it's a recent result. I guess PUG talked about it last year or this year?
Last year, yes.
Last year. Yeah. So what is known in resource theory of asymmetry is that there's this kind of a distillation dilution type of result for level pairs. So if you have a state rho, no, if you have enough copies of these unit level coherences for all the level pairs in the available coherence, then you can create rho by covariant operations. We also know that there is a sequence of correlated catalytic transformations that can create arbitrarily many copies of these guys if it's within the reachable coherence of rho. So this is just a way to prove our statement, right? We just need to show that, well, if we can merge the sequence of correlated catalytic transformations into one big thing, we can just do this and then create it, right, by number one, and that's done. And I'm super grateful for UG for hooking this up, because this is like really a lot of work. The hard work is done in a sense for us. So how do we show that we can merge this thing? A priori, it's not super clear because it's a sequence of correlated catalytic transformations, right? And I think before our work, it's not known whether catalytic transformations can be concatenated in a sense. That if you have two correlative catalytic transformations, can you combine it into one big thing? And in some sense, this is our technical contribution that we show that it's actually possible. So how do we do this? How do we show this? Well, we show we can merge it into one big thing. And the tool that we use is this new asymptotic setting that we call marginal reducibility, where instead of transforming many copies into many copies, and then this whole thing is epsilon close to product of the final thing, you just look at the marginal, that the marginal is close to the final thing. I'm going to talk more about this tomorrow in my own talk, not as a sub-speaker, but it is a tool. And so the idea is to use this result that I'm going to talk about tomorrow to somehow, this formulation is kind of general. You can use it for asymmetry. But this doesn't quite work because in asymmetry, there's bound coherence state. There are states from which you cannot distill coherences. Yeah, you cannot distill coherence. So, but if you look at the proof, it doesn't show up. No. Is it showing up here? It's showing up on my computer,
Oh, really?
but I think the screen is frozen.
Screen is frozen. Yeah, Zoom doesn't show it either.
It doesn't show it either. So maybe.
Oh, yeah, there you go. Yeah, okay. Didn't see anything. If you look at the proof closely, you see that this direction, showing that if there is a marginal, if you can transform it with this marginal reducibility thing, then you also have catalysis. This direction is actually good. And it's just because we use this very, 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 very common construction called one state, everything is good. What doesn't work, what doesn't quite work because of this bound coherence stuff is the other way around, showing that if you have catalytic transformation, then you also have this marginal reducibility thing. We do know, we can show that this direction also works for two-level systems. So if your system is only two levels, catalysis is the catalyst is also two levels, then this direction also works. And turns out this is just exactly the thing we need from this result. So then the problem now is reduced to showing that marginal reducibility is transitive. Because if it is, you can just go from catalysis to marginal reducibility, combine it into one big thing, and then go back to catalysis again, right? And this is indeed what we do, and this shows that we can merge this sequence into one big catalytic transformation. Yes, so that's the result, kind of, and the proof idea. And so now, back to thermodynamics, right? What does this mean for thermodynamics? I should have hidden this, but I guess I think what this suggests is that in correlative catalytic transformations under thermodynamics could probably, maybe, if we are lucky, be characterized by two monotones or two quantities, right? One for the free energy part with just energy considerations, and one for coherence part. And why or how we think this is possible? It's because for Gibbs preserving operations, correlative catalytic transformations is just really characterized by free energy. And this is that. And for covariant operations, well, we showed that if the direction holds, right? We don't know if the other direction also holds. I think Ryuji and Naoto's paper that is submitted concurrently to arXiv showed in some cases you also have the other way around. So we do there is some evidence that this could be true. This is the monotone that governs what transformations under covariant operations. And the next thing is that maybe in this catalytic setting for state transformations, thermal operations just exactly the intersection between Gibbs preserving operations and covariant operations, or in the sense of monotones. You just take the monotone for Gibbs preserving operations and the monotone for covariant operations, and well, you get thermal operations. Maybe any of these points, well, the first point is closed. This point and this point, solving these is like solving the conjecture. It's gonna be hard, but I think it's like it's worthwhile to explore this question. So to summarize, we studied this phenomenon of catalytic coherence manipulation, asymmetry, and therefore also somewhat into thermodynamics. And our technical contribution is showing that this marginal reducibility, or in some cases correlative catalysis, this is a transitive relation. So you can concatenate it, you can merge it into one. And the questions, well, from specific to general, are these breachable coherences actually covariant monotones, asymmetry monotones? This we don't know. Can you find this kind of phenomenon also in thermodynamics? This we also don't know, because the map that we use to amplify coherence, it's really it's a covariant map. Not sure if you can implement with thermal operations. And the last thing is, I guess, the holy grail, trying to find all the monotones for thermal operations. And with that, I close, and thank you.
Thank you very much for the nice talk. If we have time, some comments and questions, Philip, please.
Can you bring the mic up?
Oh, no, that's the one.
Okay. Thanks for the nice talk. I was curious about the thing you mentioned on the last slide, I think, or the slide before that, like about your conjecture of thermal operations being Gibbs preserving operations intersection with covariant operations. Maybe I'm missing something, but like, so maybe you can explain to me in which sense you mean that, because like if you look at even the systems without any Hamiltonian, you get, the conjecture would turn into things, something like, I mean, covariant operations just, everything is kind of covariant, right? Because I don't have any Hamiltonian. So, and in that case, the thermal operations would be something like noisy operations, and the Gibbs preserving operations would be something like unital operations, and there already is a gap at that.
Yeah.
So I was wondering if there's more besides there's some fine that they did.
Yes. So I agree. This is very, I don't know, imprecise, and you can pick a lot of bones with this. But what I just want to say is that this statement, exactly as written, I know it's wrong. It's proved in this Chwalinsky paper, right? And there's another paper, this enhanced thermal operations. But at least in this setting of state transformations, and you consider catalytic state transformations, I think it's not known. And I don't know, if you want to be more, I don't know, the sense is just, can you just take monotones for Gibbs preserving operations and covariant operations, and gives you the monotones for thermal operations? I think there's the sense that one should attack this problem. Yeah.
Are there more questions? Comments? Comments? Oh, then maybe let's go on with next speaker. So thank you, Ray.